Now this is a very long question, but each individual section should be quite straightforward, although you will find that it quite hard at this stage because you're not used to mixing topics up together. The electron enters an electric field like this, a uniform field. The electric field outside of the region may be assumed to be zero, so it's telling you that you can disregard anything outside there. The potential difference between the plates is 95, and their separation is 2.2. As the electron enters the region of the field, it is travelling parallel to the plates. So you can see it coming in this way. Okay, so you should do either something like that or that, depending on the force it feels, which is the first question. On the diagram above, draw an arrow at P to show the direction of the force acting in the electric field. Okay, so we have our electron going this way. Now we have a positive plate here, and this is an electron, so it's going to feel an attraction. So the force acting will be upwards there. So you should have a nice straight line pointing up at P. Calculate the force on an electron. Now I'm going to do a quick review session of electric fields. There were two types of electric fields that we looked at. We looked at the radial field and we looked at a uniform field. And these two had two separate relationships. The radial field had force lines that acted in this kind of arrangement. This would be, assuming this is a negative charge. And a plate had uniform lines which were equidistant. Now the relationships were a product of this kind of pattern. So for a radial field you had Q1, Q2 over R squared, and for this one you had F over Q equals E, which is the electric field strength, which is also equal to V, the voltage across the plates, divided by the distance between the plates. So these are our two important formulas. Now the question is about uniform fields, so we'll be looking at this relationship. And we can ignore the B in the middle. We are left with F over Q, force over charge, equals potential difference over distance. So calculate the force on the electron due to the electric field. You have F over Q equals V over D. So the force would be equal to the voltage, 95, over the distance, 2.2 times 10 to the minus 2, because it's in centimetres, times 1.6 times 10 to the minus 19, which is the charge. And that should give you 6.9 times 10 to the minus 16 newtons. Please remember to use units. The next question, what is the time of flight to cross the plates? Now here we have a distance of 12 centimetres. The velocity of the electron is 2.7 times 10 to the 7, and so therefore you can work out the velocity by just calculating an average speed. Distance over time would give us that speed, so 12 times 10 to the minus 2, because it's in centimetres, over 2.7 times 10 to the 7, okay, which would give us 4.4 times 10 to the minus 9. Seconds. But that's not the end of it. Okay, so let's just draw this out again so we can work out the vertical distance now moved by the electron during its passage between the plates. So what we have is two plates causing a vertical deflection S, and we have to use equations of motion for a projectile question. Now a projectile question is going to be looking at the motion vertically. So if we do SUVAT, okay, displacement is what we're looking for. The initial velocity vertically is 0. The final, we don't know. The acceleration, we don't know. And time, we worked out in the previous question. So as we can see, there's still a lot of information missing. Now, the nice thing about this question is it's taking you step by step. You've worked out the force in the previous question. So it's important when you get stuck on questions like this that you go back and look at the things that you've calculated. How can they help you? In this case, we have the force. And if you have the force and the mass, you can find the acceleration. So let's do that now. The force acting is 6.9 times 10 to the minus 16. And the mass is 9.1, which is a constant. You can look it up. You can look up 10 to the minus 31. You can look it up, of course, on the data booklet, so you don't have to go too far. And that would give you 7.5 times 10 to the 14 meters per second. Okay, so that's your acceleration. So now we can see we do have enough information to use the equations of motion. You've got A, you've got S, and you've got U, which gives us everything we need by using that relationship. So S would be half times 7.58 times 10 to the 14 times T, which was 4.4 times 10 to the minus 9, but that was squared. And your final answer should give you 7.5 times 10 to the minus 3 meters. And the next question is very common. Suggest why gravitational effects were not considered when calculating the deflection. The forces that we're dealing with have to be similar for them to affect each other. In this case, we've got a charge which is being pulled up by an electric field. Really, we should be considering the weight down. But weight here, mg, would actually be very, very small. It's times 10 to the minus 31. Okay, so the mass is of an order of 10 to the minus 31. Compared to the electric field, this is very small, and so can be treated as insignificant. Disregarded as in comparison with the electric field. Okay, so that would be your full answer, and this is a very common question. So this question just keeps going on and on. So now they've made this even more complicated by adding a magnetic field. In a mass spectrometer, remember this is a machine that uses magnetic fields to separate particles. Electric and magnetic fields are used to select charged particles of one particular speed. A uniform magnetic field is applied in the region between the plates, such that an electron passes between the plates without being deviated. So let me draw that out because it's a bit of a strange situation. So you have your parallel plates, and this is what your electron was supposed to do. That's why you were calculating vertical deflections. But now that it's telling you that because of a magnetic field, which I'll draw here, the charge is now undeflected. It's continuing in a straight line. So that must be because it feels a force down to balance the force up due to the electric field. So you have a force due to the electric field and a force due to the magnetic field. Now, how did I know to draw these field lines going into the paper? For that, you need to use the left-hand rule. But you're going to use the left-hand rule with your right hand. Now, it's important that you don't call this the right-hand rule, even though you're using the left hand, because the right-hand rule is something else. Now, if we do that, if we work out all the fields, the charge is moving this way, but it's an electron. Remember, the left-hand rule is used for conventional current, a positive charge. So if we do the reverse and we work it out for the electron, you will work out backwards using the force down, which you figured out from the balance situation, and use the current moving in this direction. You should end up with the answer into the paper. So if we look at the question and the marks allocated, you would get 1 mark for saying force acting downwards and using the left-hand rule. For an electron, the magnetic field is acting into the paper. So now we need to determine the magnitude. So as you can see here, we have F equals BQV, 6.9 times 10 to the minus 16 from a previous question, because it balances the up force. If you remember, here, if that force equals that force, then we know the magnitude of the magnetic force, and you rearrange to give a field strength of 1.6 times 10 to the minus 4 Tesla. Sure, that's clear enough. There you go. And finally, part G. So if we consider the particle undeflected like that, it asks what would happen if this particle was going faster. Well, if the particle was going faster, then our magnetic field would be the only one affected. Because remember, it's the only one whose relationship has a V in it. So if it goes faster, this force downwards would be bigger. And so therefore the deflection would be greater in this direction, down. Then it asks, what would happen if this was a positive charge? Well, you'd have to go right back to the beginning of the question, because everything would be very different. Our initial deflection would now not be towards 95 volts, the positive 95. It would be in the opposite direction, because now this would be positive, so it would be attracted to this plate, and so that force would be down. This time you could use the left-hand rule, because we're dealing with conventional charges and current, and you would find that your B, your F, due to the magnetic field, was still equal to the electric field, but this time they were reversed. The outcome would be the same. It would continue in a straight line because these two are balanced. And finally, we finish this question. Now we've got some multiple choice questions. And this is just a simple left-hand rule question. If you use the 3 fingers to try and figure out predict the way that the direction that this foil would move, your current is conventional in this direction, your field is pointing south, so you should be able to identify that the direction is up when you use the left-hand rule. Now this is a tricky question. You have 4 wires. Some of them are leaving the paper. Here they have current flowing up, up and down and down. And you need to consider what the resultant force acting at P is. Now in order to do that, you need to think about these field lines. Using the right-hand corkscrew rule, then you just consider what would happen if these field lines arrived at P. They would either act clockwise or anti-clockwise. So I'm going to draw those in to make things easier. And I'll show you on this one so you can see what I'm doing. If we use the right-hand corkscrew rule, you can see that this force field is acting in a clockwise direction. So if it was projected outwards, by the time it reached P, you would have to draw that force at a tangent to the circle. Okay, but you can see that the force due to this wire is that way. So if you do that for all 4 wires, you would see that these four forces are acting. This force has field lines acting this way, which creates this force at P. This one has a force field line pattern going that way, which creates that force. This one has a force field pattern that way. So we have 2 forces acting that way, 2 forces acting that way. If you remember our vector addition, this plus this would equal the resultant in this direction. So the answer is D. So in this question, field lines of force represent the magnetic field, and you can see a field line pattern here. State whether the field strength at A and B is constant, increasing or decreasing. So you should know that the distance between the lines indicates the field strength. So at A, the field strength is constant, and at B, you can see that the distance between them is increasing. So it is decreasing. Explain why field lines can never touch or cross. This is kind of a silly question, but sometimes you get that in the IB. How do we know that they never touch or cross? Because if the field lines show you the way a force is acting, if the force is acting in if the lines were crossing, so if they did something like that, then that poor particle in there would be feeling forces in 2 separate directions, and that does not happen. So if lines touched, okay, you would have an impossible situation, something which is quite a difficult thing to do, to say in physics, that something's impossible. But nonetheless, that is your 2 marks. Oops, I'm just going to leave that there. So here we have a bubble chamber, and as it explains in the question, it's just a simple apparatus that shows the way the particles move. You get a high energy particle coming into the cloud chamber or bubble chamber, and at P there's a reaction that makes 2 charged particles exist, and their tracks are shown below. Now this is all caused because of some kind of force field. And you should by now be able to identify, because it's a curve, because we get this circular motion, it must be due to a magnetic field. If it was electric, you would have a deflection that way or that way, but never this curving stuff. Now, as it mentions in the question, you have 2 charges. One of them moves in one direction, the other one moves in the other direction. The magnetic field that they apply would be constant, either out of the paper or into the paper. So what's different about these 2 charges? Well, FBQV, that stays the same because it's the same magnetic field. It must be that the charge is different, and that's what it is. You have a plus and a minus. The third one, also quite a common and easy question. The path is a spiral. It should be a circle because the force is constant. However, something must be decreasing because its motion is is becoming smaller, per se. The radius of that circle it's moving is becoming smaller. So if we look at our relationship, the magnetic field's not changing again, the charge is not changing, the speed of the particle is decreasing. And it's decreasing because there's probably other particles in here. It's in a bubble chamber, so there's some liquid. So there's collisions, it loses energy. Okay, so as it loses energy, it loses kinetic energy and it loses speed. So energy lost. Right, we've got a positive charge inside a uniform magnetic field, and it's parallel to the direction of the magnetic field. This is kind of a trick question because it's saying velocity is parallel to the direction. As you know, using the left-hand rule, everything has to be at 90 degrees. The magnetic field must be at 90 degrees to the current, which will end up being 90 degrees to the force. So if it's parallel, there's zero force. Another way of looking at it is BQV. This sign part would actually have to be used, and this would give you a 0. So the answer to that question is A. So here we have a straight conductor in the plane of a uniform field. The current is not at 90 degrees. So we need to find out exactly how much of that is. What is it actually asking for? The current in the conductor is I. There's an angle to the magnetic field. The force per unit length is P. Write an expression for the magnetic field strength. So the magnetic field strength can be found by rearranging this formula. Bill, sine. Now if we rearrange it into the correct form, and we can see that the force, as it mentions here, the force per unit length can be replaced as P. So we end up with P over I sine of the angle. And by that angle, make sure that you are clear, is the angle between the current and the magnetic field. Okay, so they have given you the correct angle. I've never seen a question where they give you the wrong angle, but just be careful with that. So the answer to this must be C. Now on the website, I already have a video that explains this in a lot more detail. So if you're not clear on how the motor works, then I suggest you watch that video. In this question, they would like you to draw connections from the battery to the split ring. So you need to show some kind of connection there, but not touching. Okay, so that you show that there's a connection with a potential for disconnection. Let me draw that a little bit more neatly. Now important things to note on this diagram is that this is the positive terminal, so therefore conventional current would dictate that this current is flowing that way, and then through the wire it's flowing that way. This enables the force to be found as moving down on this side and up on this side. Okay, so you've got your north-south direction that way, your current flowing that way, and using the left-hand rule, you should be able to identify that this coil moves down and this one moves up. For this question, have a look at the video that's on the web page. Alright, with this question, I made a complete mess of scanning this in, so I'm just going to have to use the pictures and ignore everything that's written. But what you've got here is a little motor. Okay, and you remember magnets, magnetic field strengths are very important for motors because the force that's created depends on the magnetic field. But anyway, this is a pulley, so as the motor spins, this will be pulled up. Okay, this weight would be pulled up, but let's not forget that there is a force acting down, which is the weight. Okay, so you would have force due to the magnetic field and force due to the gravitational field. And then, surprise, surprise, it asks you to draw a labelled free body diagram. Now, what do we remember about free body diagrams? That the forces must go through the object and they must represent the sizes. So, how is this moving? It's accelerating uniformly up. So, you need to show that in your forces. So, what have you got on here? We have a force up, which is due to the tension in the string. And that force is bigger than the weight down, mg. And what we can see is that tension is much bigger than mg. So what happens next? We have the weight, because we have the mass. They give us a mass of 15 grams. They tell us it takes 2.2 seconds to go up a height of 0.84. So I don't know what they're asking, but there's going to be equations of motion in it. Calculate the tension of the thread as the weight is being raised. Right, so that's a summation of forces, isn't it? Because you know from this that there's two forces acting. So summation of forces, F equals ma, summation of, there. So summation of forces, T minus mg equals ma. Right, but what's ma? We don't know the acceleration, but that's why they're giving us all these numbers. So let's solve at this. The object starts off at rest, so it's 0. Who knows its final velocity? A, we don't know, but we're going to find it. And S is 0.84 meters and T is 2.2. So let's work this out to give us an A of 0.35 meters per second. And we found that using S equals ut plus half at squared. Okay, once we know that, once we can substitute that value into acceleration, then we substitute all the other values in, and we should get a force, a tension of 0.16 newtons. So we have a solenoid. Which one of the following diagrams best represents the magnetic field pattern due to an electric current? So this is something you're just going to have to remember off by heart. We have the same magnetic field pattern that we would expect around a bar magnet. Okay, so north and south. So that's on the outside. Which one of these would represent what's happening inside? Well, it's inside the coil, you have a uniform magnetic field. And it would only start changing as you move away from the center. So this one's okay, but these are still uniform. You wouldn't expect that because we're moving away from the magnetic field. These two are utter nonsense because you wouldn't get a change inside the coil. So the answer is A.